Hello everyone, my name is JunKyu and I'm presenting the work Transprecise Object Detection to Maximize Real-Time Accuracy on the Edge. The collaborators include Blasen Bargis, Roger Woods, Hans van der Donk. We are all from Queen's University Belfast, and this work was supported by CHIS ERA DeepWeb project. The idea of edge computing is in locating the edge device near to the data to realize low latency response time or minimize the data size sent to the cloud by pre-processing the data on the edge devices. So edge devices can be utilized in either edge-only mode or hybrid mode. In edge-only mode, the edge device itself performs real-time video analytics, and in hybrid mode, the edge device is connected to the cloud. Particularly, edge computing is fitted to real-time video analytics. First, real-time video analytics requires low latency response time. For example, when undesirable anomaly activities are detected such as smoke, fire, suspicious person activities, etc., then the immediate actions should be taken. Second, sending real-time video streaming data to the cloud requires high bandwidth between the camera and the cloud. By pre-processing the video stream data on the edge located near to the data and just sending the metadata to the cloud, the required bandwidth can be significantly reduced. However, in general, edge is limited in compute resource, leading to longer inference latency from a deep neural network. As a consequence, a longer latency incurs modular frames, degrading the real-time object detection accuracy. This slide discusses a real-time video analytics example using the edge device, which is an NVIDIA Jetson Nano. We picked smart social distancing example. The link to the project is shown in this slide. The idea of the project is basically to detect people and signal the alarm when people violate the social distancing rule. In the picture, the people who violate the rule are shown with the red boxes. The analytics data are shown in right side. In this example, there are 434 violations within 1 hour and 8 violations within 1 minute in this supermarket. When the violation rate is high, an appropriate action can be taken immediately. In this case, detection and its analytics are done on the edge device, Jetson Nano, which is located near to the data. By doing so, it is not necessary for the edge device to communicate with the cloud. As indicated in the previous example, implementing full object detection on the edge is a desirable approach for real-time video analytics. First, low latency response time can be realized. For example, the edge can signal the social distancing rule violations immediately. Second, for further analysis, the metadata instead of raw video data can be sent to the cloud. This minimizes the data size sent to the cloud for hybrid mode video analytics applications. As mentioned earlier, due to limited compute resource from the edge, the main concern in implementing full object detection on the edge is in the achievable accuracy. We noticed that real-time video input stream data have dynamic features in terms of object size and object moving speed, and we can leverage such dynamic features to improve the accuracy. For example, some people are close to the camera and some people are fading away from the camera. In this case, the size of detected objects are dynamically varied. Therefore, our approach switches multiple deep neural networks dynamically according to dynamic input features in order to maximize the real-time object detection accuracy. Several attempts to maximize accuracy by switching neural networks on the fly were proposed previously. For example, in 2018, Jiang et al. Proposed a framework that switches deep neural networks on the fly by assessing the inference accuracy periodically during runtime. Since an extra highly accurate deep neural network is used for periodical accuracy assessment, it is not suitable for the resource-constrained edge devices. Another approach to maximize accuracy was proposed by Marco et al. In 2018. The idea was to employ an extra lightweight inference engine to select an appropriate deep neural network during runtime. This approach was used for image classification. This approach was not fitted to real-time object detection approach, since even small increment of inference latency would hurt real-time object detection accuracy significantly. Therefore, the runtime decision-making for real-time object detection applications should have negligible time and negligible space overhead. Hence, we propose a proactive runtime decision-making approach that has negligible space and time overhead. Our approach basically leverages the research findings proposed from machine learning and embedded system community. For the first exploitable property, when the object sizes are relatively large, a lightweight deep neural network has equivalent performance with a heavyweight deep neural network. As the second property, when an object moves slower, the drop frames rarely affect the detection accuracy. For the third property, hyperparameter search returns an optimal hyperparameter set for a model based on training data set. Based on the three properties, we conclude that the runtime decision can be based on the hyperparameter search outcome with the parameters of the object size. The contribution of our work to the edge computing community is twofold. First, our approach will help low latency edge-only mode real-time video analytics. Second, our approach can minimize data size sent to the cloud for hybrid mode real-time video analytics. This slide discusses our runtime decision-making approach framework. We named this framework as Transprecise Object Detection Framework, TOD for short. TOD exploits the different accuracy characteristics across multiple deep neural networks. In our experimental setup, we utilized the 4 different YOLO models that use deep neural networks for their inferences. Since we do not want the time overhead when TOD switches a network, we pre-wrote the 4 YOLO models as an initialization process. Then after the pre-loading, runtime scheduler selects an appropriate YOLO model on the fly according to the object size detected from the real-time video stream data. I will discuss further in the next slide about how the runtime scheduler schedules the deep neural network deployment based on the object size detected and how the runtime selection is related to the object speed. To determine the runtime selection policy, we employ the hyperparameter search method. The hyperparameter search assesses the accuracy for each hyperparameter set with the training data set and returns the hyperparameter set which has the best accuracy. Each hyperparameter represents a median of the detected object size in each frame. We choose the median of the object size over the average of the object size for the runtime selection, since the median can be more robust against the false positives of the average. Our hyperparameter search employs 3 parameters since we have 4 different neural networks. For example, if the median size is smaller than H1, the runtime scheduler selects YOLO B4416, and if the size is between H1 and H2, the runtime scheduler selects YOLO B4288, and so on. This slide describes our experimental setup. We utilize an NVIDIA Jetson Nano board with max power mode. For the object detectors, 4 different YOLO models are used. Each model was optimized using TensorRT to obtain higher performance on our NVIDIA Jetson Nano. We utilize an open dataset, which is Multi-Object Tracking 2017 detection dataset, MOD 17DET for short. The MOD 17DET open dataset also provides an accuracy evaluation toolkit, so we utilize it to assess the real-time object detection accuracy. Finally, to measure power and GPU utilization during runtime, we utilize an NVIDIA Tegra Stats tool. This slide discusses the accuracy gain by our framework TOD. In the offline object detection accuracy, the most heavyweight DNN, YOLO B4416, showed the superior accuracy for all the datasets since it did not suffer from the drop frames. However, if it applies to real-time applications, the heavyweight slow DNN suffers from the accuracy drops due to the drop frames. For example, for the three datasets in the figure, most 17-02, 04, and 10 that contain small-sized walking people detected by static cameras, YOLO B4416 kept the best accuracy. However, for another dataset, another YOLO algorithm shows superior accuracy over YOLO B4416. In such cases, either detected bounding boxes for people become larger or people move faster compared to the static camera cases containing small-sized walking people. Our runtime scheduler can be fitted to each case. However, in our experimental setup, we seek the best decision policy over all the different cases in the entire dataset. As a result, TOD obtained superior average accuracy over entire dataset compared to each YOLO model. For example, TOD achieves the 35% accuracy gain compared to the YOLO before Tiny 288 detector. TOD is also beneficial in terms of power saving. With most 17-05 dataset, we measure the power consumption required for each YOLO model. For example, YOLO Tiny version models require 4 to 5 watts, while YOLO full version models require 7 to 8 watts. Since TOD utilizes all the 4 YOLO models, TOD consumes 3 to 8 watts depending on the runtime decision. TOD requires only 63% of the power without losing accuracy compared to YOLO version 4.416 model. This slide describes the details of deployment usage of each DNN according to each dataset. For example, in the static camera case, which is most 17-04 dataset, the variation of the object size is small, resulting in keeping one YOLO detector. However, in the case of a most 17-11 dataset, the object size variation is high. As a consequence, all the 4 YOLO models are deployed. The memory budget by TOD requires just 11% more than one single YOLO B4416 model. Therefore, TOD achieves accuracy gain by sacrificing minor memory budget. Notice that the impact of this overhead on the inference latency is negligible, since the memory allocation reserves such memory spaces prior to the execution, and TOD assesses each YOLO model stored in DRAM as required. This slide includes some demonstration when objects are fading away from the camera. In this case, objects are getting smaller and the runtime scheduler chooses a heavier deep neural network over a current neural network. In the top side figures, when the objects are fading away and the current YOLO model is YOLO B4288, our TOD decides to switch the current YOLO model to YOLO B4416, which is heavier than the current YOLO model. The same situation is shown for YOLO Tiny version models at the bottom side figures. For conclusions, TOD selects a deep neural network on the fly based on real-time video stream features such as object size and object moving speed. TOD maximizes real-time object detection accuracy on the edge device, which is a Jetson Nano. Finally, TOD also saves the power consumption compared to a full YOLO model without losing accuracy. This work was supported by the two projects, OPRECOM and DPAT. Thank you very much for listening to my presentation.